Okay, so I'll start with introducing myself. For those of you that know me, my name is Terry Blackburn, and I've had the pleasure of supervising Graham Edwards' PhD research over the last 5 years. Graham joined us in 2016, and it's been a great pleasure of mine to get to work with him. I should start and thank everyone for being here, especially the graduate committee, which includes Miriam and Slavic. So today's a celebratory day for Graham, but it's also a somber day for all of us here because we have to say goodbye to him. He's done a tremendous amount, not just writing, the 5 or 6 papers that he either led was the lead author or co-author on, but he supervised undergraduate research and he made our lab work. He helped us calibrate our instruments and calibrate our tracers and worked on algorithms for uncertainty propagation. And he's a name that we're going to remember in this lab for years to come. And everyone will know his name and revere his work. And so he set a very, very high bar for us. And so I don't know what we're going to do without him, but I do know that he has a very bright future in front of him. And he's going to tell us about some of the more exciting ideas that he has led. He's really led these ideas for himself over the last couple of years. And I look forward and hope you guys get to enjoy seeing what Graham has done. And so with that, I'll turn it over to Graham.
Thanks, Terry, for that super kind introduction. Making me feel good going into this. I appreciate it. I'm gonna just do the screen sharing and safety muting to make sure we are avoid any Zoom kerfuffles. So great. So yeah, thanks again, Terry. That was super nice. Thanks everyone for tuning in. I'm really, really excited to be sharing some of my dissertation work with you today. And so it looks like I've got I've got a floating cursor. Can everyone else see this floating cursor?
Yes.
Okay, cool. I'm gonna kill that, and I'm gonna try to do this slideshow again. Sorry about that. Okay, and it looks like it's showing up every time I start the slideshow. So that is the Zoom curse of today. I'm going to try just rebooting this very quickly. Oh, goodness. Okay. Folks, unfortunately, I'm gonna have to ask you all to just like take 5 because I'm having PowerPoint issues. Sorry about that.
So to take the pressure off of Graham, I'm going to apologize, Terry. I really, truly didn't realize that my position on the committee didn't change. Or I assumed it changed because you are now tenured professor. So
that I can handle that.
It's okay. I mean, I can do whatever is necessary, but.
You'd probably have to file like revised paperwork or whatever to get it officially changed or something. But
yeah, there would have been like I think with timing it would have been a lot of somersaults. So thanks for rolling with the punches, Slavic.
Always.
Whew. All right, folks, we are in business, it looks to
Great.
be. Okay, back over to, oh my goodness gracious, no.
I think Terry doesn't want you to finish.
That's exactly true. But
Is
it
that-
also should be said that I have gotten him just the very best computers. This is not my fault.
No. This is totally me having been messing around with PowerPoint all morning, and now in the clutch it gets hung up. But I think we're in business now. Okay, awesome. Okay, cool. All right, second try. Let's go. So thanks for tuning into my dissertation, folks. So today I am going to take you through some of my research. My research during my dissertation has spanned a broad range of timeframes and a broad range of geologic settings. But the unifying link that holds this all together is the use of uranium as a geochronometer, of using uranium as an atomic clock to track time in Earth and planetary history. And so uranium has been used now for like 100 years plus to measure time in a bunch of different Earth systems. And it's an incredibly useful chemical tracer for time. And the utility of uranium was realized over a century ago now by the really foundational work of Marie Curie in characterizing radioactive decay. And then she was followed by these geologists and chemists who then expanded these principles of radioactivity, like Arthur Holmes and Ernest Rutherford, to use that chronometric capacity. So fast forward 100 years, I've been able to follow up on the great work of folks before me and apply uranium to measure time in the deep crust of the Earth, within the interiors of asteroids, beneath glaciers and ice sheets in Antarctica, and in the far north. And so today, I'm just going to focus on two of these studies. And I'll start right off by going into the first part, where I look at thermal histories of planetary interiors in deep time. And so in this study and in these deep time studies, I'm using the uranium-lead system. So isotopes of uranium decay to stable isotopes of lead over billion to 100 million to billion year timescales. And for folks who aren't familiar with isotopes, isotopes are simply different masses of the same element. So here, for example, I have a helium atom. That's the helium-4 isotope. And so, excuse me, the interior of the atom's nucleus is made up of protons, which determine the element, and neutrons, which contribute with those protons to the mass of the element, or the mass of that isotope. So there are 2 protons, 2 neutrons, and so that's 4 nucleus particles, and so that gives it a mass number of 4. I use helium here because it's a nice, simple, straightforward isotope. The isotopes of uranium have 238 and 235 of these protons and neutrons between them. So they'd be a lot larger to look at. But now we know from studies of radioactivity that we can mathematically model the decay of these radioisotopes to their stable daughters. And so over these billion-year timescales, uranium isotopes decay away. The longer half-life of uranium-238 makes it decay more slowly. And as these decay away, their daughter isotopes of lead fill in to take their place as those decay products. Now, by taking the ratios of each of these parents relative to their daughter, we can calculate a unique date from those ratios. Now, in order to have those ratios be meaningful, we need to work in systems that start our system out with 0 lead or with some initial lead composition that we can account for. So to get to that 0 starting point, we use uranium-lead thermochronology, and that's going to be the focus of this first study I talk about. So uranium-lead thermochronometers are minerals that their crystal lattices lose lead by diffusion at high temperatures. So as long as these minerals are hot, they lose lead. They'll lose lead. But then if we let them cool down Upon cooling, lead is no longer able to diffuse out of them. And so once these minerals have cooled, they start retaining lead and recording time. And as they record time, we can then measure those lead isotopes and calculate a cooling age from those isotope ratios. And it's important to know that these are cooling ages rather than formation ages. And so this is the approach I'm going to use in my first study that uses uranium-lead thermochronology, which is titled Accretion of a Large LL Parent Planetesimal from a Recently Formed Chondral Population. And so in this study, I use lead-lead thermochronology of chondrite meteorites to show that some of the first asteroids were large and that they formed rapidly. Okay. So I'm gonna set the scene here. We are in the protoplanetary disk of our solar system. So this is an enormous gaseous and dusty disk that's orbiting and accreting onto our protosun. And in time, this is in the first few million years of our solar system, which relative to the present is 4.567 billion years ago. And we set this time zero based at the time of the formation of the first solids of our solar system, which are called calcium aluminum inclusions, or CAIs. And during this time period, planetary accretion is underway. So in its most simple form, accretion is the accumulation of particles into a more massive object under the influence of gravity, as well as a few other minor processes. And so you start with this dust, and that dust accretes to planetesimals that are a kilometer to hundreds of kilometers. Those planetesimals accrete into protoplanets, which are hundreds of kilometers to thousands of kilometers. And then those finally become the familiar planets, which are thousands of kilometers across. However, in this gradual coagulative process of accretion, as things come together to progressively larger and larger bodies, there are some barriers that obstruct this accretion process, these physical barriers. So the first one is the bounce barrier. And this happens to things that are about 1 millimeter in size. That's about the size of a large sand grain, sorry. And so at that size, things start to bounce off of each other rather than stick together. But even more troublesome to accretion is this meter-sized barrier, where 1 meter-sized bodies, so bodies about the size of a boulder, as those are traveling through that protoplanetary disk, the gas drag force, or the friction of that gas on those bodies, slows them down, and that slowing them down causes them to drift inwards toward the sun. And if they don't accrete to the sun within 1,000 years, they'll end up probably crashing into one another as they start changing their trajectories that will also disrupt those boulders into smaller pieces. And so there are these problems, these barriers to planetesimal accretion, yet I'm giving this talk to you on the planet Earth, so clearly we got past this, but it would be really nice to know how. And so since we got past this, we do know that we have this primary planetesimal population, and these are assumed to have a canonical radius of about 50 kilometers. And today, the asteroids, which live in the asteroid belt between the orbits of Mars and Jupiter, these are the remnants of those planetesimals and protoplanets that were neither ejected from the solar system nor accreted to the sun or planets. And most of the meteorites we receive on Earth come from the asteroid belt, including the chondrites, which I'll talk about in this study. And so, as remnants of this accretionary epoch and fragments of the first planetesimals, asteroidal meteorites provide windows into these protoplanetary disk processes. So today, I'm going to ask and try and answer, when were barriers to accretion passed, how were they passed, and how large were these first asteroids? So to do this, I'm going to think about two radioisotope systems. The first is our good old friend, the uranium-lead systems, and I'm going to be calculating cooling ages using the lead isotopes. I'm also going to be considering the short-lived chronometer, the short-lived radioisotope aluminum-26, which was only around during the first 5 or so million years of our solar system because it has a very short half-life. Its half-life is less than 1 million years, so it decays very rapidly. That means it's only able really to record time for a brief period of time, but because it's decaying so rapidly, it generates a lot of radioactive heat, a lot of radiogenic heat, and so it's a critical heat source for these small early formed bodies. And so, so the first thing to think about are these chondrules. So this is kind of this millimeter scale, sand grain size pieces. And so we haven't gotten to the meter barrier yet. So these millimeter scale chondrules are these spheroidal igneous droplets, which means they're crystallized from a melt in low gravity. So molten rock that cools and crystallizes within the protoplanetary disk environment. And from aluminum-26 chronometry, we know that chondrules formed about 2 to 3 million years after CAIs. And then those chondrules were accreted onto the parent bodies of chondrites. So chondrites are meteorites that are the fragments of these primitive, undifferentiated parent asteroids. And so by undifferentiated, I mean that they never underwent melting and they never separated out a metal core from a silicate mantle like our Earth has. And so you'll recall that these chondrite parent bodies have a canonical assumed radius of about 50 kilometers. And then after these things accreted, internal radiogenic heating, mostly from aluminum-26 decay, and self-insulation across the radii of these bodies created a metamorphic gradient, where the innermost material reached high temperatures. And as you got further out, it didn't get quite as hot. And so the warmest innermost material are these type 6s, and the outermost we call type 3s. And because we've got this layer, this thermal layering here, we describe this model as the onion shell model. And so in this study, we're going to focus on the LL ordinary chondrites because these are best characterized for their chondrules in terms of aluminum magnesium. And we're going to try and assess the relationship between the LL chondrites and their constituent chondrules. And so to use this, to approach this, I'm going to use lead phosphate thermochronology within these LL chondrites. And so these phosphate minerals are good lead thermochronometers at temperatures above 500 degrees Celsius. And we predict with an onion shell model that there'll be an inverse correlation between petrologic type and the cooling age. And so as we start in our outermost layers, we're going to cool early on. And as we get deeper into that body, it's going to take longer and longer to cool. There's also these type 7 chondrites that reflect near surface heating by impacts, but these are outliers, and I'm not going to go into detail on those today. And so in this approach here, I'm going to use the lead-lead thermochronology of phosphate minerals to determine the time scales of cooling in LL chondrites. I'm going to use these thermal models and measured thermochronologic data to infer the LL parent body size and when it accreted. Then I'm going to compare that timescale of accretion with chondrule formation to see if there's a relationship between these. And so to approach this, I crush chondrites, I isolate the phosphates, I then dissolve those phosphate grains, purify the uranium lead, and measure the isotopic ratios on a mass spectrometer. And so here are our dates. Up here is our modeled, our idealized onion shell body, where it gradually cools to younger and younger ages as you get further inside of it. And here's our measured data. And you'll note that all of the type 5s are older than the type 6s. And so this confirms our onion shell model. Whoops. And so now that we have an onion shell model, we can start to explore these thermal models a little bit more carefully and a little bit more meticulously. And two important measured values that I want you to keep in mind is the youngest age, the minimum age of the type 6s, and an at least 30 million year cooling duration between the oldest type 6 and the youngest type 6, which I'll call delta LL6 age. And these values are important because the duration of cooling of a chondrite of a undifferentiated body is going to scale with the size of that body. So larger bodies take longer to cool, right? You can imagine heating up a potato and a pea in an oven, and you take the two out. That pea is going to cool a lot faster to its center than the potato. And so here's some more thermal model results. On the x-axis, I have the modeled planetesimal radius. And as we increase that radius, the cooling date in the center of the body gets younger and younger. And as I increase the radius, that duration of cooling of the body gets longer and longer, as you would expect as we expand that body size. Great. So now I'm going to dive a little bit deeper into the weeds of these thermal models and kind of explore how much information we can get out of these. So here I show a suite of modeled conditions and results where I, on the x-axis, model a range of aluminum-26 contents. So the more aluminum we have, the more heat is put into the body. The less there is, the less heat. And then on the y-axis, there's the radius of the planetesimal. So small bodies down here and bigger bodies up here. And then the color coding is the model duration of that type 6 cooling. And so for big bodies with lots of aluminum, it takes a long time for that interior to cool. And for smaller bodies with very little aluminum-26, it takes less time for them to cool. And then we can superimpose on here some known constraints. So this red curve here is showing the solidus, or the melting temperature of the body. And so we know that the body didn't melt, so we know it must be cooler than this red line. We also know that it took at least 30 million years for that type 6 interior to cool, so we need to be on this side of this gray line. And our central date requires us to be above this blue line. So this gives us an acceptable region of accretion, of body size and aluminum-26 at the time of accretion. And note, and importantly, this central date requires a body with at least 150 kilometer radius. So that's a bigger body than usually assumed. So then now expanding this model to look at how aluminum-26 relates to the accretion time and comparing this accretion time to the initial aluminum-26 contents of these very pristine chondrules from the Semarcona LL chondrite, it shows that the majority of chondrules formed at the same time that our body needed to be accreting by. And so this says that chondrule formation and the accretion event had to have been happening very close in time to one another and was probably reflecting this one single event of chondrule formation followed promptly by accretion. And because of this single rapid energetic event, it means that we probably just leaped across our meter barrier rather than having to wait and get stuck at it. And so our results add to this growing body of work that's adding support to this idea that the chondrite parent planetesimals were very large when they first formed, hundreds of kilometers in diameter, and that they accreted from a very recently formed chondrule population, and that the meter barrier was rapidly crossed. So if you want to hear more about this, this was published in Science Advances in 2020. It's an open access journal, so anyone can go there and check it out to learn more. But that's not going to be the end of my talk today, because I want to take you 4.5 billion years closer to the present. And we're going to look at subglacial processes in the Quaternary. So that's just the last 2.5 million years. And so if we're going to look at things on these timescales, we want to take a closer look at the uranium-lead system. Before, we were assuming that uranium isotopes decayed directly to the stable lead isotopes. But this decay systematic is a little bit more complicated than that, because we have these decay chains where we decay from our parent to our stable daughter through a series of intermediate daughter products. And so these intermediate components tend to be pretty inconsequential for dates greater than 10 million years, like our chondrite dates. But they're really, really important for things at the million-year scale, or especially any date that's less than 600,000 years. And so in the research I talk about today, we're just going to look at these first two long-lived daughter isotopes of uranium-238. So there's uranium-234 and 230 thorium. And both of these have half-lives of about 100,000 years. So that makes them ideal for measuring time on 100,000-year timescales. And so one way we can think about these reservoirs of each radionuclide through these decay chains to make it a little bit easier on us is to think of each reservoir of the radionuclides as a sequence of draining tanks. So we start with our initial parent uranium-238, and that's always kind of gradually decaying and producing uranium-234. And that uranium-234 is also radioactive, so that decays and produces thorium-230, and so on and so on. And so what happens is that on long time scales, this infill and outgrowth of these isotopes converges the ratios of these onto a secular equilibrium, this sort of long-term equilibrium value that will reach for the system on timescales of about 1.5 million years or longer. And so here you can see that we take not the atomic ratio, but by parentheses, I'm denoting an activity ratio of uranium-234 to its parent uranium-238. And you can see in this model that it will sit at a value of 1, which is secular equilibrium for any activity ratio, and it'll sit at this value of 1 indefinitely. The same thing happens for any adjacent radioisotope pair. So uranium-234 and 230, it will also sit at a value of 1. Of course, lead doesn't follow this rule because it's a stable daughter product, and that's where everything kind of stops and lead continuously grows in. But today we're going to be focusing on 230 and 234, these two isotopes. And so we start at circular equilibrium, but then let's say some geologic process empties the thorium bucket. And so that's going to move our ratio down to 0. But over time, that bucket's going to start to refill, and it's going to gradually grow back up. And eventually, that bucket will fill enough that its outgrowth will balance out the ingrowth, and we'll be back at a value of 1 and stay there indefinitely. And so I talked about this geologic process to separate thorium, and water is a great process for that, and how we incorporate uranium into water lane or aqueous precipitates. And so uranium is very soluble in water, typically, and thorium is very insoluble in waters. And so this is going to remove thorium out of the water column. And then if we start to form a mineral precipitate out of that water, it's only going to take up uranium. And so now we have a crystal with a mineral crystal with just uranium in it. And over time, that uranium-234 is going to decay to 230, and it'll grow in and be able to tell time for us. So this is the framework we're going to use to do uranium-thorium dating of subglacial aqueous environments. And this study that I'm using it in is going to be is called a terrestrial record of subglacial melting beneath the northern Laurentide ice sheet. And so the overview here is that Heinrich events, which I'll tell you a little bit more about soon, these were important ice loss events for the now extinct Laurentide ice sheet. And precipitate rocks from Baffin Island in northern Canada record subglacial melting during Heinrich events and indicate a shared stimulus by ocean warming. Okay, so the importance of this study is that it is really important in the context of modern anthropogenic climate change to understand how the Earth climate system changes and different parts of it respond to those changes. And so ice sheets are a very important part of this Earth climate system because these things influence and respond to perturbations in the atmospheres, oceans, and the solid Earth. And so today, there are currently 2 ice sheets on Earth, the Greenland ice sheet and the Antarctic ice sheet. But ice volumes on the Earth's surface and on the continents has changed through times. And if we're going to understand it has changed through geologic time. And if we're going to understand how the Earth system is going to change moving into the future, then we need to be able to look back and understand how the Earth system has changed in the past. And so if we look back just 20,000 years, we go from our modern ice configuration. And going back 20,000 years, the northern hemisphere had these large ice sheets, a Eurasian ice sheet covering the northern part of Eurasia, and the Laurentide ice sheet covering the northern part of North America. And between 20,000 years and 10,000 years, those large global ice volumes plummeted from maximum glacial conditions, and within that 10,000 year window, nearly got to the modern configuration. But that didn't just happen in that one instance, because ice ages have been coming and going. These glacial periods, these maximum glacial conditions have been coming and going throughout the Pleistocene, or the last 2.5 million years. So in this plot here, I show time relative to a record of ocean oxygen isotope ratio. So this delta 18 oxygen, this is measured in the skeletons of little critters from the seafloor. And those are basically these oxygen ratios are recording essentially how much ice is on the continents. And so when the compositions go into these red regions, these are warm interglacials where there's little continental ice volume. And as they go down into these blue regions, these are glacial conditions. These are large continental ice volumes and cooler glacial climates. And notice that these are occurring on about 100,000 year timescales. All right, so we're going in and out of these ice ages at about the timescale of 100,000 years. But now, if we zoom in, there's also variability at the millennial scale. All right, so that's the 1,000-year time scale. And so this plot here is showing a record from the Greenland ice sheet. So this is an ice core from the Greenland ice sheet. We're showing the oxygen isotope ratios of the, the oxygen isotope ratios of the ice. And so what this is instead measuring is not the continental ice volumes, but it's actually telling us about the air temperature in Greenland. So here in the Holocene, we have more positive ratios. And that means we've got a warmer climate, right? The last 10,000 years is our current interglacial, the Holocene, pretty warm temperate climates. But if we go back in time, we see that as we drop into the last glacial, we get to lower isotope ratios, which means colder conditions. But within these cooler glacial conditions, we have these cycles between warm and cold that are called Dansgaard-Oeschger cycles. And so there are these warm interstadials, and I'll use a red or pink for an interstadial, and these cooler stadials, which I'm going to use a blue color for. So you can see that going through this record, we have these peaks of warmth and these usually longer durations of cool stadial conditions. And so these have implications for the climate system. So it's not just warm temperature, right? There's a whole suite of Earth climate system things going on. So during these warm interstadial conditions, what's happening is there is an enhanced North Atlantic current. So the North Atlantic current, which begins in the Gulf Stream, is this surface current of warm, salty waters coming up from the equator. And those make their way up into the North Atlantic. And so as they make their way far north, they bring warmth with them. So that makes the air warmer over Greenland. They also bring more salt to the North Atlantic. So it's a saltier North Atlantic. And those two things together help to reduce the sea ice extent in the Nordic seas. And they also enhance this North Atlantic deep water formation. So this deep water formation is driven by the salty water in the far north, and it drives this deep sea, deep ocean convection of water, and it cycles ocean water through the deep ocean globally. And so during these interstadials, we've got enhanced North Atlantic deep water formation, which drives a strong Atlantic meridional overturning circulation, or AMOC. Now, if we go to the stadials, it's the flip side of these. So stadials have cool air over Greenland. So during these stadials, there's a reduced North Atlantic current, which brings less salt and allows for more fresh water in the North Atlantic. There's expanded sea ice extent in the Nordic seas. And because there's less of this salty water getting up to the far north, you have reduced deep water formation and a weak Atlantic meridional overturning circulation. So these are the sort of cycles that we're going in and out of from cooler to warmer conditions over the course of these glacial conditions. But there's another quasi-periodic or a cycle-like type of event called Heinrich events. And so these are these quasi-periodic episodes of ice-rafted detritus deposition. So ice-rafted detritus are these coarse, large, more sandy, pebbly, rocky pieces of sediment that can't make it far out into the ocean just by the power of rivers. So instead, they need to be carried out to sea by icebergs. And icebergs are great at taking this large, heavy material out into the deep ocean because as the ice sheets travel across the land, they pick up a bunch of sediment and debris, and then they carry them out past their grounding lines out into the ocean on ice shelves. And then as icebergs calve off of their ice shelves, they're released as Heinrich events. And then as those icebergs melt, they release that debris and it can collect in layers on the seafloor. And so we know Heinrich events have to be these iceberg swarms that are disgorged from these northern hemisphere ice sheets because these ice-rafted debris, Heinrich events, are widespread across the North Atlantic. And they're seen in many different cores from many different areas in the North Atlantic. So we know this is a really large scale event. And based on the composition of that ice-rafted debris, we think most of it comes from the Hudson Strait. And so the Hudson Strait is really important because this is where the Hudson Strait ice stream is. And for folks not familiar with ice streams, these are these regions of really fast moving ice within an ice sheet. And so these can move at rates of a kilometer or several kilometers per year, which is really fast for ice. And these ice streams are discharging the majority of an ice sheet's ice and sediment. And the Hudson Strait ice stream, this was the big one for the Laurentide ice sheet. It was the largest ice stream of the Laurentide ice sheet, and it was a really important ice stream for regulating the amount of ice in the Laurentide ice sheet. And so looking back at these Heinrich events, let's start to take a look at their timing. So they recur about every 7,000 years, but the time frame in between them varies. And all of these Heinrich events are overlapping with stadials. So you'll see here, right, that these pink bars represent interstadials, and each of these peaks is falling in the context of a stadial. And so if we look at the greater climatological context of these Heinrich events, we also see these exaggerated stadial conditions. So there's very reduced North Atlantic current and very reduced deep water formation. There's a very weak overturning circulation. Some folks think it might even be shutting off for the most part during this time. And that means we've got a very fresh North Atlantic, and we've got expanded perennial sea ice extent in the Nordic seas. And so these Heinrich events are these important ice loss events for the Laurentide ice sheet. They're a really important part of these Earth system climate processes, and yet we don't know really well what causes them. We have a couple models that have been proposed to try and explain these things. So the first is an internal model that looks at just how the ice sheet, it might be controlling its own ice growth and ice loss. And so this is called the binge purge model. And in this model, it assumes that the Hudson Strait ice stream sits on a bed of loose sediment. So it's almost like the ice stream is sitting on a bunch of marbles, and it can slide across those marbles if the bed is unfrozen. But if we start at a thin ice sheet state, that bed is going to be frozen, and there's going to be no basal sliding. And so that sluggish ice is going to gradually accumulate volume. But then eventually the ice sheet gets thick enough. And when ice sheet gets thick, two important things happen. The first is that with all that thickness, it can insulate the bed and help to keep heat down there. The other thing is that ice is an incredible molecule that melts when you put pressure on it. And so you can see here that the crystal structure of ice, of frozen water, is open. And if you squeeze it, you can kind of make that structure collapse, and you can drive melting. And so just by putting a really heavy ice sheet on top of the base, you can actually drive melting at the base. And so if our ice sheet thickens enough, it'll start to melt at the bed, and the ice stream will accelerate on this lubricated base, and you'll have rapid ice loss, releasing IRDs, or releasing icebergs, and that is our Heinrich event. And eventually it thins out enough that we return to our initial state. And based on these models, this binge purge cycle can repeat about every 7 years. Another model looks to ocean forcing. It says the ice sheet is going to be the ice sheet processes are not going to be internally controlled as much as they're going to be really driven by changes in the ocean system and how ocean is delivering heat. So recall that during stadials, there's reduced northward surface heat transport, right? We've got a weaker North Atlantic current. And so warming at the equator, that heat has nowhere to go. And so it starts mixing down into the subsurface and then starts to shoal or shallow in the North Atlantic, where it can start nipping at the edge of the Laurentide ice sheet. And even more importantly, it might be starting to melt away these ice shelves in the Labrador Sea and Baffin Bay. And as those ice shelves melt away, we lose this buttressing, and the Hudson Strait ice stream is not supported by those fronts. And so it starts to surge and disgorge icebergs, which we know as a Heinrich event. And we are and the role of this subsurface warming seems pretty important, because these folks, Marcotte and others in 2011, they showed that a temperature proxy, a way of tracking temperature in the intermediate subsurface depths that are important for this process, are coinciding perfectly with Heinrich events in all the places that they measure them over the course of the last glacial. So this subsurface warming in the ocean is coinciding with North Atlantic debris pulses. And so this seems that they must be closely related. However, Heinrich event records include ocean sediments, climate proxies, and ice sheet models, but there are no terrestrial archives of these ice sheet processes. And it would be really nice to have something that's on the ice sheet or in close proximity to the ice sheet to be able to tell us, what's driving this? How is the ice sheet responding during these Heinrich events in situ? And so we look to the subglacial environment, and I'm going to ask, what can the subglacial environment tell us about the Laurentide ice sheet dynamics? And I'm going to show you in these following slides that the role of ocean forcing in driving Heinrich events is super important. And so for this study, we are going to look at the Barnes ice cap. So the Barnes ice cap is on Baffin Island in northern Canada, up here just across from Greenland. And this is one of the last vestiges of the Laurentide ice sheet. And only about 100 or so kilometers away from Barnes ice cap are these suite of local marine terminating ice streams. So of course there's no ice streams there now, but during the last glacial maximum, there were a bunch of ice streams along the coast here that were draining out from the Laurentide ice sheet. And these had glacial maximum grounding lines up to 1,000 meters below modern sea level, which would have put them right in contact with these subsurface waters and would have made them very sensitive to these warming events. And so this is a good place to test these models. And near the Barnes ice cap, there are these subglacially formed carbonate precipitates. And so these are calcite cemented precipitates that form on the lee or down ice flow sides of boulders and undulations. And they're about LGM in age, so they're about 20,000 years old. And so the reason these things form is because beneath your ice sheet, you have some melting in the up ice area that brings water down to the other side of these undulations. And as the ice gets to the other side of these undulations, because the ice is flowing this way, it pulls the ice away from here, which reduces the pressure. And remember how when we add pressure, we melt. Well, when we remove pressure, we'll freeze. And so at these down ice locations, the ice starts freezing and it's just gonna pull water out of there, right? Ice doesn't want to incorporate salt. And so we start concentrating the salts in this water, and that drives cryoconcentration and calcite precipitation. And that's how we're making all of these, different sorts of calcite precipitates. Great. So with these calcite precipitates, I can break off portions of them, dissolve those, isolate the uranium and thorium, and measure those uranium and thorium isotopes to try and calculate uranium-thorium dates. Great. So I look at 6 different samples. 5 come from the Barnes ice cap margin, and 1 of them comes from this area to the north and west of the Rimrock Hills region. And so these are sand and silt that are cemented with calcite. And so remember how before I talked about these waterland precipitates being just pure calcite? Well, trouble comes along when we start incorporating sediments in them or making these dirty carbonates. So when detritus is incorporated into this precipitate mineral, remember how when thorium goes out of solution, it's going to grab something solid, right? It's going to go into those sediments. And so thorium is grabbing onto these sediments. So then when we add these sediments to this crystal, there's going to be this detrital component of thorium that is then going to be contributed to our authigenic, or our sort of in situ formed calcite precipitate. However, although 230 thorium is our daughter isotope that we really want to be keeping track of, we also have another isotope of thorium, the thorium-232, which is, it is radioactive, but it has a 14 billion year half-life. It has an extremely long half-life and takes a very, very long time to decay. And so thorium-232 is essentially stable on these timescales. And so we can actually track that detrital component using thorium-232 and help us account for any inherited 230 thorium. Awesome. Okay, so within our dirty carbonate, we've got a mixture of authigenic isotopes, right? That stuff that came out of the water, mixed with detrital isotopes, which are coming out of the sediment. And so if I break off a number of pieces of my sample and I dissolve and measure each of them, I can plot these, the isotopic compositions, with our 232 thorium that's detrital, relative to our authigenic 238 uranium. And then I'll plot those against the daughter to parent isotope. And so if these array out in a line like this means we can model this mixture with a line that we call an isochron. And that isochron is telling us that these are all the same age. And so if we drive this isochron to 0, where our detrital component then is 0, we can actually calculate a detrital-free end member or to put it another way, the pure authogenic end member that we can calculate an age from. And so, because we have 4 isotopes, we're going to need 3 different axes. And 4 isotopes make 3 axes because one of those isotopes is going to go into the denominator of our ratio. Cool. Okay. So now we can present this in 2 different ways. These isotopes, or sorry, we can present these uranium thorium isochrons in one of 2 different ways. If we measure a number of samples that have an authogenic and detrital component mixture, right? These pink dots are going to be our measured values. And using those 3 pink dots, we can either regress a uranium-238 free detrital composition with a Roche-Schultz diagram, or we can regress a thorium-232 free authogenic composition with an Osmond diagram. And so the Roche-Schultz has everything over thorium-232, and the Osmond has everything over uranium-238. And so in order to sort of look a little bit more carefully and make it easier to look at this 3-dimensional isochron, we project it into 2 dimensions. So to do that projection, I'm going to take our 3-dimensional data, and I'm going to flatten it against our 232 versus 234 axis, our 232 versus 234 plane. And then I'm going to rotate that plane, and that's going to show us just what this one little slice of our graph looks like. And in that slice, we can calculate our authogenic 234 component. And then we can do exactly the same thing with 230 thorium. And that way, through 2 different panels that are these 2 different projections, we can calculate both of our authogenic end members and calculate a full date from there. With a Roche-Schultz diagram, we're going to do exactly the same thing, but now we're calculating the detrital compositions that we can then subtract from our measured compositions to calculate an authogenic value and a true authogenic date. Awesome. So now we've got 2 diagrams that are actually mathematically equivalent. So I'm going to use the Osmond diagrams to start out with all of this data because that better shows the scatter of the data, and they show, more insightful isochron usually. However, Roche-Schultz diagrams help to visualize these detrital contributions. So I'm going to use those when we wanted to explore what the detrital contribution is. And when we explore those detrital components, we're going to assess whether or not we need to correct for this detritus. And so if we regress a non-zero detrital composition, we'll need to correct for that. But if we regress a detrital composition of 0, then we don't need to correct for that. And so those will be tricks we'll use or techniques that we'll use to help calculate robust, really defensible uranium thorium ages for these complicated carbonate systems. Great. So I'm not going to belabor going through this data here. I'm going to show you a series of plots and isochrons. They also have strontium isotope compositions included, but I'm not going to talk about that today. So some of them regress really nice isochrons with reasonably precise dates. Others have no uranium contribution, but do have a thorium detrital contribution that we need to account for. Some of them show different behaviors between the different sort of morphologies and the different types of those samples. And then some of them have layers. And these layered samples are really exciting because those might have the opportunity to tell time in them. So this is that sample from the Rimrock Hills region, and we use isochrons on parts of it and account for and can show that there's no detrital component for other parts of it. We can even plot our dates versus our thorium-230, 232, right? That's a good tracer for a detrital contribution. And we see that there's no trend with this. There's no there's no leverage that any thorium-rich component is having on these. So these are pretty reasonable dates without correction. But then when we compare them to the stratigraphy, right? So these are dates corresponding to the stratigraphy of this sample. There's really no trend. There's no single, it's not getting older or younger in one direction. And so what this tells us is that this calcite is forming in a single episode with a little bit of noise. In contrast, this sample from the Barnes ice cap margin, we calculate these nice radiogenic dates for them. This was a much easier sample to work with. It had a really high, it was really radiogenic. We were able to calculate, uncorrected dates for the upper layer A. We were able to get a really good date from this lower layer B. And it records a history across 6,000 years, over 6,000 years. So this lowermost layer is forming around 30,000 years. And then this upper layer is forming across about 1,000, 1,500 years, over 4,000 years after that lower layer formed. And so now we can take all of our data and put it together. And it shows that we have these precise pulses of calcite formations that are occurring during Heinrich events. And so these calcite forming events on central Baffin Island are corresponding tightly with Heinrich events. And I'm going to take some time now to go through and show you how they compare to some of these different proxies of millennial scale climate variation and Heinrich events. So up here is on this uppermost part is a good old friend. This is that northern Greenland ice core record. And remember that values up here are warmer conditions and values down here are cooler conditions. And these red bars are corresponding with those warm interstadial events. And now these blue bars, these are identifying the Heinrich events. And so if we look in these stadials where these Heinrich events are occurring, we see that they overlap really nicely with our calcite forming events. If we go one record down, we can see these Hulu cave speleothems in green. So speleothems are cave deposits. These are cave deposits from China, and they're responding to the seasonal Asian monsoon intensity. And through some of the wondrous teleconnections of Earth's climate, the Asian monsoon intensity is really closely linked to northern Greenland temperature and these sort of climate variabilities in the Earth system. And so when we get these low dips in the Hulu Cave record, these are Heinrich events. And so you can see that these Heinrich events are, again, lining up very cleanly with our calcite forming events on central Baffin Island. And then you'll remember that during Heinrich events, the Laurentide ice sheet is releasing a ton of icebergs. It's releasing a bunch of meltwater into the North Atlantic. So here in blue, we have a North Atlantic freshwater proxy. And you can see that there's increases in freshwater input into the North Atlantic during these Heinrich events. That's also corresponding with the formation of this calcite. In addition, if we look at ice rafted debris, we can see this ice rafted debris record is matching up closely. And then we can also see that during these little local peaks in subsurface warming, these are corresponding with calcite forming events. Now, they correspond really well with the H1 and the H3 calcite forming event, but the record is missing here at Heinrich 2. And so what we can do is we can look to another record actually in the southern hemisphere from the West Antarctic Ice Sheet Divide Core. So this is going to be a similar sort of thing to the Greenland core. It's an oxygen isotope record from the water and the ice. And so as it goes up, it's tracking local warmth, and as it goes down, it's tracking local cooling. And you can actually see little peaks in this record that slightly lag each of these warming peaks in the North Atlantic. And if we account for that lag at this little peak that shows up here, we can actually see a local warming event corresponding to this IRD event and this calcite forming event here. So we have a 3 out of 3 coherence between calcite formation and all of these Heinrich records. I'll note that this is a relatively short-lived calcite forming event over a much longer Heinrich event. And so clearly there's something a little bit exciting, something a little bit different going on here. Why is this shutting off early? And what's going on here is this is the glacial termination. That's the end of the ice age. The whole ice sheet is starting to collapse through this interval here. And so this is just a different sort of thing going on right here. And there's some really interesting stuff to talk about around that. I won't have time to talk about it in this talk right now. I'll be glad to talk about it later. Okay, so it's important now to come back to how are these precipitates forming? We know that they need liquid water to form. And so how are we getting this water here? Well, we know that a thickened ice sheet should drive basal melting. And so if we look at an ice sheet thickness model, and these things are being driven by ice sheet thickness, that would be a possible result. But if we look at these reconstructions of ice sheet thickness, they're really stable through this time frame, right? We see these pulses of calcite formation, but at Barnes ice cap, this white curve here, the ice sheet is staying really, really stable over this time frame. And so it can't be thickening. So we're going to need another process. And that process is going to be shear heating. So as ice starts to flow, right, ice is a viscous fluid and it flows through an ice sheet. And as that ice is flowing past itself, is flowing around itself and flowing past, the molecules are flowing past one another, it's going to generate heat. You can almost think about it as like when you rub your hands together and it warms them up and you're generating friction. This is kind of what's happening as those ice molecules move past each other and they're generating heat with that motion. And so if we have a mechanism to drive shear heating, that is a great way to drive basal melting. And of course, a great way to drive shear heating is ice stream acceleration, is ice acceleration from ice streaming. So remember, we have all these ice streams reaching out into Baffin Bay during the last glacial. And so if subsurface warming comes up and starts to nip at their grounding lines, they're going to start to retreat. And as they retreat, that ice is going to thin out near the margin. It's going to thin out and move out into an ice shelf. And as you thin the ice here, it steepens your slope, and that's going to drive faster and faster ice flow. And as you speed up that ice flow, you're going to drive warming, especially at the base, and that warming can then drive melting. And we know that this ice acceleration needs to be locally driven. This can't be some far afield effect from the Hudson Strait ice stream. And the reason we know this is that this region of the Laurentide ice sheet is really insensitive to what's going on everywhere else. So this map over here in color is showing us where the Barnes ice cap is and where Hudson Strait and the Hudson Strait ice stream is. This dome here is called Fox Dome. And Fox Dome feeds this way into the Hudson Strait ice stream and feeds this way to Barnes ice cap. In this panel, this shows an ice thickness change between the last glacial maximum and almost the end of that big termination period, that 10,000 years of termination. And so dark colors show large decreases in ice thickness over 400 meters of ice thickness loss, and light colors show little to no ice thickness loss. And so you'll see that this area, over the course of this time period of extreme ice loss, this area stayed really stable. So even when we have lesser accelerations of the Hudson Strait ice stream, this area should not be having ice acceleration affected by it much at all. And so that means it needs to be this local ice stream driven process. And so what this means is we have two locations that are independently accelerating ice streams and driving local basal melting and lubrication in response to ocean subsurface warming. And that tells us that this is likely the most important trigger for driving these Heinrich events. And it really validates this ocean forcing stimulus as the driver for our Heinrich events. And so that brings me to the end of my talk. I hope I've been able to show you some of the incredible ways that uranium has allowed us to look into Earth's past and understand these Earth and planetary processes. Of course, I owe a great debt to the foundational work of these scientists over a century ago. But I also just want to take this moment to thank some other really important folks and scientists in my life and who made this all possible. So I want to thank Terry Blackburn, my advisor, for all the mentorship and all the guidance and answering so many questions and posing so many questions that all helped me really grow as a scientist. I want to thank my mom, Sarah Edwards, for instilling my love of science in me at probably around this age that you can see, taking me out into the woods and the fields and getting me excited about natural history. And then just the biggest thanks I want to give out to my lab mate, Gavin. One could not ask for a better friend or colleague. Thank you so much for all the great science over these last 5 years and all the boondoggles we've gone on. And I'm looking forward to more to come. And with that, there's so many other folks I need to thank. Thank you, everyone on here and others who I couldn't even list for all the scientific and personal support through these last 5 years. So thank you all for your time, and I'd love to answer some questions.
Thanks, Graham.
Thank you.
Yeah, why don't we take any questions from the audience? You can put them in the chat, or you can unmute yourself and.
Hi, Graham.
Hi.
Awesome job. Yeah, I really liked that. And I thought your figures were so beautiful and I understood everything so well. Thank you.
Thank you.
I had a question about your method for determining like the ages using the ratios in the calcite precipitates. So I know that like in the ocean, thorium likes to stick to your canonical marine particles. And you mentioned that they also stick to the particles that come from IRD. So I was wondering if you have to worry about thorium scavenging or adsorbing onto your calcite mineral interface, or if it just doesn't stick that much as it sticks to IRD and other particles in the marine system.
Yeah. So those subglacial sediments, those are going to scavenge all the thorium that's being produced in those subglacial waters. So yeah, those bring a bunch of thorium into our subglacial precipitates. And so yeah, that's why using those isochrons is really critical. Some of these are quite radiogenic despite having a significant detrital component. But yeah, all of those isochrons are needed to really account for that thorium component that's being incorporated and brought into those calcites in the subglacial system. And the reason that even though that thorium is going in there attached to sediments, that thorium isn't really like in the calcite. In order to date the calcite, we need to dissolve it, and we use strong acids, and those strong acids then start pulling the thorium off of the sediment surfaces. So in a way, like, yeah, if we could just get the calcite off of there and not touch the surfaces of those sediments at all, we'd be doing great. But that's just, that's the way to get the calcite dissolved is also going to pull that thorium off of the sediment. And so that's why we need to account for it with those isochrons.
Cool, thank you.
Hey, I have a question.
Yeah.
So my first question is, I've seen predictions of future warming leading to a slower AMOC, in part due to like the freshwater hosing effect from glacial melts. And I was wondering like if you could comment on how these warmer events that you're talking about in the past had a stronger AMOC.
So the interstadials have a stronger AMOC because those are correlated with a stronger North Atlantic current. Now the Heinrichs are occurring during stadials. So Heinrichs are actually relatively cold periods. But what's warm about them is subsurface ocean warming. So the reason that the Heinrichs are driving this melting and the iceberg surges is not because you've got warmer air temperatures, but because you've got poor surface transport on the ocean, and that's allowing this subsurface turbulent mixing of warm water that sort of works its way northward and then starts to shoal in the North Atlantic where it attacks the glacial margin. And certainly like this is adding to a body of knowledge that certainly we're kind of in this place where we know that ocean warming can be really important for marine terminating glaciers. And so, like what we're showing here is that, it was just as important for the Laurentide ice sheet.
Great, thanks. I do have one other question. I might be asking you to speculate a bit on this one, if that's okay.
Sure.
Yeah, so you talk about how in your first section, the chondrules just easily let past this meter barrier. And I was wondering why you think that is they were so easily able to cross it.
Yeah, that's a great question. How they crossed it, I don't know. There are lots of ideas out there that can kind of work for it. But what's happening, or what seems to be happening, is that the chondrules are being produced by an energetic event. Something that's putting energy into a system, right, they're being melted out of this dust. So you've got a lot of heat going into that system. And when you also have high energy events, sometimes you have these like shock events and these these high pressure like shockwave events called bow shocks are one model for forming chondrules. If you add these, pressure perturbations in a region, you can start to cluster material, and that can drive rapid accretion. So these energetic events can, just in the same way they form chondrules and drive melting of this material, they can also then trigger this, this sort of matter collapse that will drive really rapid accretion to large sizes.
Awesome, thank you.
Hi, Graham. Great job.
Thank you.
Congratulations. I have a question actually about so following up on the interstadial Heinrich event question that Will had. And so you present a really interesting mechanism for sort of collapsing, I guess. Like if they accelerate, you'd think that the ice sheets are collapsing. But then at the same time, you also said that the height of the ice sheet wouldn't be changing much during these intervals.
Yeah.
Sea level is only rising at the end of the Heinrich stadials. So can you square that for me, please?
Yeah. I will do the best that I can. So the sort of acceleration and surging that I think is happening in Baffin Bay is to a much lesser degree than the surging that's happening in the Hudson Strait ice stream. So that's a much larger ice stream, draining a much larger area with just a lot more, much more ice sheet bed. And so that's like the Hudson Strait ice stream is really like the big player behind the Heinrich events. In terms of the ice magnitude change to the north and east of the Fox Dome, I think that is probably pretty minor. Like you certainly have ice loss to some degree, but it is not a termination style degree. And the Heinrich events themselves, well, they are important events with ice loss and iceberg calving. They are not individual Heinrich events are not terminations or ice sheet collapse events, with the sort of exception of Heinrich 1 kind of conspicuously overlapping that termination, and folks have certainly debated how important of a role it plays. If that answers your question, I can wax more.
more open questions. That's good. Thanks.
Thank you.
All right. If there are not any more questions from the general audience, we can give Graham another round of applause, and then we'll go ahead and say goodbye to everyone, and the committee will hang out with Graham for a little bit.
Thanks, everyone.
Awesome job, Graham.
Congrats, Graham.
Thank you. And for folks on the YouTube stream, I'm going to end the stream now, but thank you so much for tuning in.